Acoustics is the science or study of sound and refers to its transmission through various media, such as air or water. Architectural acoustics deals with the effects of enclosed boundaries on sound. In order to understand acoustics, one must have a full understanding of sound pressure waves, how they propagate, and how the brain interprets sound. Architectural acoustics can be divided into three main disciplines: room acoustics, sound isolation, and engineered acoustics. Room acoustics can be defined as the behavior of sound when it is produced in an enclosed space. Sound behaves much differently in a room compared to an open-air or free-field environment such as a football field. It is very important to understand that the audio system is at the mercy of the acoustics of the room where it is located. No audio system can compensate for poor room acoustics. Remember, acoustics first, then audio. Like all forms of energy, sound waves continue to propagate until they have been dissipated in air or they have been absorbed. As such, when produced in a room, sound waves reflect off of walls or any other hard objects in their path until they decrease in energy level to inaudibility. Discrete or distinct reflections are known as echoes and behave in a predictable manner. Based on the source location and the angle the sound pressure wave strikes a surface, we can calculate the location to where a reflection will travel. The angle of incidence always equals the angle of reflection. By placing acoustic treatment at the point of reflection, we can modify how the sound reacts to the surface. Reverberation consists of multiple reflections traveling in various directions within a room. RT60 is a measurement that represents the time it takes reverberation to decay 60 dB. It is referred to as the room's reverberation time. Reverberation time is the primary metric by which room acoustics are measured. Generally, rooms with a high RT60 are conducive to slower traditional styles of music, while rooms with a low RT60 are best for speech and contemporary music. The challenge for the acoustical engineer is to generate a design that is conducive to a specific purpose. A concert hall design, for example, is vastly different from that of a multi-purpose room or a worship center. The length of reverberation in a space depends largely on two variables: room size and the finished materials in the space. Normally, the larger the room, the longer the reverberation time will be. The RT60 can be modified by installing soft absorptive materials in the space that have a moderate to high absorption coefficient. The absorption coefficient is a single number rating between 0 and 1 that represents how much sound a material can absorb at a particular frequency. The amount of absorption a material has is commonly referred to as its noise reduction coefficient, or NRC. The NRC is an average of the material's absorption coefficients at 500, 1000, and 2000 Hz. Keep this in mind as it does not fully represent the absorptive nature at low and high frequencies. There are two main classes of sound-absorbing materials which utilize different methods for absorbing sound: porous absorbers and resonant absorbers. From these, we will discuss the three most common: adiabatic, diaphragmatic, and absorption by resonance. Adiabatic are porous absorbers that consist mainly of fiberglass and mineral wool panels. This type of absorption is inherent in draperies, clothing, and furniture. Interestingly, they absorb by converting the sound energy into heat. They are most effective for absorbing mid and high frequencies. Adiabatic absorbers are the most common type of acoustical product used to lower a room's reverberation time and to control reflections. Commonly known as bass traps, diaphragmatic absorbers rely on a resonating diaphragm to absorb energy. When low-frequency energy hits a diaphragmatic absorber, it causes the diaphragm to vibrate, which absorbs that energy. These absorbers have a high absorption coefficient in the low frequencies, but will reflect high-frequency energy. Helmholtz resonators work in the same yet inverse manner of a soda bottle when one blows across the opening. The air inside resonates at a particular frequency known as its resonant frequency. When this occurs, the air inside vibrates, dissipating sound at that frequency. The absorbed frequencies are dependent upon the size of the opening and the cubic volume of the bottle. Helmholtz resonators are extremely frequency specific and are very effective at absorbing sound at one particular frequency. Diffusion is considered the opposite of absorption. It can be defined as the scattering of sound waves by reflecting them in various directions or breaking them into smaller pieces. Diffusion is commonly used to limit or eliminate specular reflections and echo without adding absorption to the room. Diffusion is also used to direct sound energy to specific areas. The two main types of diffusers are the barrel diffuser and the quadratic diffuser. Both types of diffusers work equally well in their specific applications. The barrel diffuser is a rigid element that incorporates a large radius, which results in what appears to be a barrel cut in half. When sound waves strike this round shape, they reflect off of various points on the surface, sending them in various directions. Pyramid diffusers work on the same principle but use offset angles that form a pyramid. Quadratic diffusers diffuse reflections by forcing the sound to travel different lengths before reflecting back into the space. Typically found in recording studios, the quadratic diffuser tends to be much smaller physically and possesses a distinctively elegant look. Early reflections are those which reach the listener's ear within 30 milliseconds of the direct sound. These reflections are beneficial to the listener. Early reflections contain information about the size of the space and the location of the source and are crucial to speech intelligibility. Late reflections are those that reach the listener's ear 85 milliseconds or later after the direct sound. Late reflections degrade speech intelligibility and make contemporary music sound jumbled and confusing. Adding diffusion and/or absorption panels in critical listening spaces will eliminate late reflections and help to achieve a proper acoustical response. Speech intelligibility is how well the spoken word is understood by a listener in the acoustical environment. This is affected by several acoustical conditions in a room, including reverberation time, the amount of early reflections, and the ratio of direct to reverberant sound. Speech intelligibility is best when the reverberation time is low and the listener receives early reflections. The DR ratio is a direct comparison of the amount of direct sound to reverberant sound reaching the audience. This is very important in determining speech intelligibility. If the audience is receiving more reverberant sound than direct sound, it will be difficult to understand speech. This is due to multiple reflections in the reverberant sound field arriving at the listener's ear within a relatively short time frame. Acoustical modeling allows professionals to efficiently create the space virtually in order to solve real-world issues. Powerful modeling software packages perform in-depth calculations for nearly all important acoustical characteristics. Building acoustics is primarily concerned with sound isolation between adjacent spaces and between indoors and out. Limiting the amount of sound transmission between areas is the principal objective. It is important to understand that sound absorption and sound isolation are two completely different concepts. Installing absorption panels on the wall to quiet the neighbor's drum kit is highly ineffective because they are not designed to stop sound transmission. Sound transmission level is lowered by adding mass, damping, and airspace to the dividing partition. Transmission loss of a partition describes how much sound level is lost when passing through a partition. The less sound passing through equates to a higher transmission loss. Transmission loss is quantified by a single number rating known as STC, or Sound Transmission Class. STC is a laboratory rating of a material's ability to prevent the transmission of sound. STC is measured by producing noise in one room while measuring how much sound is able to pass through the test specimen in an adjacent room. The higher the STC, the less sound passes through. A material's STC is critical when attempting to reduce or eliminate sound from traveling between two spaces. Sound can take many paths to reach adjacent locations other than the direct path. These routes are known as flanking paths and exist due to the rigid connection of walls, floors, and ceilings to one another. In order to eliminate flanking paths, these rigid connections need to be replaced or retrofitted with resilient damping materials. Inserting rubber, neoprene, compressed fiberglass, or even cork into a flanking path will decouple the path, greatly reducing the amount of energy transferred from the source. For instance, if an aerobics room were located above a classroom, spring isolating the suspended ceiling in the classroom would help reduce the direct sound path. Adding a floating floor in the aerobics room would help reduce both the flanking and direct paths, thereby increasing the transmission loss between the two spaces. If a classroom was located beside a band practice room, attaching an additional double layer of sheetrock hung with rubber isolators and attaching it to the ceiling using a resilient acoustical sealant would provide increased mass, airspace, and damping required for increased transmission loss. Engineered acoustics is primarily concerned with achieving low noise output levels from the heating, ventilation, and air conditioning systems. There are many sources of noise within the HVAC systems, ranging from fans and motors to air turbulence and air diffuser noise. Critical listening spaces such as sanctuaries, classrooms, libraries, and conference rooms should be free of excessive mechanical noise. Noise criteria, or NC, is a single-number rating system used to quantify the amount of noise being produced by the mechanical systems in a given space. These criteria provide a range of expected noise levels for specific rooms. As noted on the chart, critical listening spaces require a low NC. The acoustics in a space are largely responsible for how the audio signal is perceived. Poor acoustics cannot be fixed with an audio system. It is important to note that a room's acoustical characteristics and the audio system work together and should be equally matched. Acoustical properties and characteristics must be considered when designing a critical space such as a sanctuary, an auditorium, or a performing arts space. By way of an experienced acoustical engineer, existing acoustical concerns and issues can be resolved by conducting a detailed study and applying the appropriate acoustical products.